что пережил первую часть сегодняшнего дня, но не факт, что переживете следующую. Сейчас будет, на мой взгляд, один из самых интересных тьюториалов сегодняшней программы, а именно тьюториал по безопасности. Вещь, в общем, редкая и очень полезная. И, в общем, до какой-то степени хорошо, что здесь чуть меньше народу, чем наверху, потому что вы сможете задать все свои вопросы и не отпускать этого прекрасного человека очень долго. Вот. Собственно говоря, Магнус — человек, который очень много занимается вопросами безопасности в Postgres, в том числе, поскольку он занимается инфраструктурными всякими вопросами, он много на эту тему всяких вещей знает и сделал. Вот. И это, в общем-то, первый в своем роде такой длинный тьюториал по безопасности Postgres вообще, не только в России, но, в принципе, обычно где-то бывали какие-то доклады, например, у нас в прошлом году, тоже от Магнуса. Но народ сразу сказал, что ну, что-то как-то мало и неинтересно. Тут только начали, а тут, понимаете, только закончили. Поэтому в этом году мы попросили Магнуса подготовить более обстоятельную историю. Ну и помимо этого вы можете просто сразу участвовать в дискуссии, спрашивать какие-то вопросы. So I switch to English a bit to explain some organization things. If you have a question, just raise your hand, and there are some microphones here, and our assistants will bring the microphone to you. The purpose of that is we have video recording, and because of that it's necessary to speak really loud using microphone to have your question on tape. And the second thing about that is that we will have videos on our site probably in 2 weeks or so. Then they will be prepared, cut, and ready for publication. So please ask your questions using microphones. And let me introduce Magnus. I already told a bit in Russian about who you are. You can just say a few words about that, and I think you will enjoy his talk. And welcome, Magnus, here in St. Petersburg.
Okay, thank you. I hope Ilya didn't say too many bad things there when he introduced me in Russian. I have no idea, of course, but we'll trust him on that. And again, as he mentioned as well, you're more than welcome. Please ask questions during the presentation. Don't necessarily wait until the very end, because then we'll have forgotten what we were talking about. Do we actually have someone who can turn on this?
Already in progress.
It's in progress? Okay. Eventually we will have slides here that will tell you the title of my talk, the reason I'm here, which is a Postgres security primer. Let me just ask, how many of you in here were at this event last year? Oh, okay, just a couple. Okay, that's it. How many of those of you went to my talk at that event? Okay, so good for you. This is more or less, it's the same kind of topic, but a tutorial instead of a talk. So hopefully more content, hopefully still useful content. A few quick words about me. I think we're getting slides. Yes, we have slides. Okay, now you can all point out my spelling mistakes. As Ilya said, my name is Magnus Hagander. I'm a member of the Postgres core team, along with Bruce, who had the previous session, and 4 or 5 other people, 4 I think at this point. I'm one of the Postgres committers. As I like to say this year, you're more than happy to heckle me for not doing enough of that, because I've not been enough convinced to the next version, but hopefully next time. And I also do a lot of work for Postgres Europe, the umbrella organization around Europe, which we do actually include Russia in that, but I don't think we're doing much activities with Russians, because you already have strong local user groups here, so you don't really need us. But we run the main big conference events, the Postgres Conference Europe and those things, and just generally help out local user groups. So when I don't do Postgres work, I work for a company called Redpill Linpro, which is an open source consultancy and services company that's based in the Scandinavian region. I am out of Stockholm in Sweden myself, so actually fairly close to here compared to some of the other speakers. where I work in our department for infrastructure services as the main sort of database consultant guy doing database consultancy, trainings, lots of trainings. We do 24/7 support, all those kinds of things, focused on Postgres. We do actually have some people who do, you know, MySQL and those evil things, but I try to leave that to other people and get rid of it myself. So, for this talk about security. Security is hard. Right? Okay, we're done. Here we go home now. That's sort of the number one thing. It really is pretty hard to do security right. If you actually look at a lot of people, sometimes I end up going out to clients and doing like a security review of whatever deployments and things they're doing, if they have sensitive things in their database, and very, very few people actually get it right. A lot of people get it part of the way right, and then sometimes they top that off with something really wrong and just negate everything they just did. Whereas some people will actually get it completely right. But the thing is, there is no such thing as really one thing that's right. If it was that simple, then, you know, the marketing messages you get from the security companies would actually be true. And we all know, you know, marketing messages tend to not be true. In usual, there is no one solution to sort of the concept of security, whether it's, you know, database security, Postgres security, or just security at any level. In fact, there is usually not just one requirement. It really depends on who you are. And that's what I find usually one of the very first spots where people just get it wrong. Is they'll go to someone and say, you know, can you please build me something that's secure? Or, you know, fix my security. And it doesn't work that way. You have to start by realizing, okay, so what do you actually want to secure against? What do you need to protect against? What are the potential attacks that can happen against your system? Same thing from a reliability perspective, of course. What can break? What will happen if it breaks? In this case, is it important? I've worked a lot with public sector organizations in Sweden before, particularly, where they all said, well, all our information is public information. We don't really need security. Like, all this is public data. Anyone can come to us and get the data. Yes, but can they come to you and modify the data? And they're like, oh, yeah, maybe it's actually important to do something about that. So it all comes down to requirements, right? And Postgres provides you with a toolbox. It provides you actually with a very good toolbox. It contains a lot of tools. It contains, I'd say, more tools than most other databases. Maybe not all of them, but most of them. You definitely don't need everything. I think anyone who deploys every single security feature that's in Postgres is doing something wrong. Right? Those requirements, they don't exist. In fact, in a lot of cases, maybe you don't actually need anything. In reality, most of the time, you're going to need something that, you know, it's somewhere in between those two. It's not going to be everything. It's not going to be nothing. It's going to be the right amount that you need. And of course, it's also about taking those features and actually deploying them the right way, not just putting them in there. So looking through the kind of things that I figured we'd talk a bit about today is, I'm going to start talking about the environment, because Postgres is only as strong as the environment that you run it in. Then I'm going to look at communications security, and specifically around the areas of authentication, which is one of Postgres' strong points compared to many other systems. I'm going to spend most of my time, I think, I have no idea how much time, depends on your questions, in the areas of sort of this infrastructure level security in Postgres. But in the end, we're going to look a little bit at the things that we can do within the application. Now, we could probably spend a week talking about just the kind of things that we can do in the application. So I'm not going to do that part. I'm not going to, exciting as it is, we're looking at new things like row-level security coming up in the next version of Postgres. I'm not going to talk about that. This is all about things that actually exist today. There might be some sessions, I haven't actually looked properly at the schedule, that talks about things like row-level security during the rest of the conference. So we'll see about that. But these are the main things that we're going to look at. And we're going to start looking and talking about the environment side. Because if you're going to secure Postgres, it can never get more secure than the environment that it runs in. If somebody else is in control of the operating system that you run Postgres on, then there is nothing you can do. Whether that means that somebody else is running the operating system for you, or that somebody else has hacked the operating system and taken control of it. Once that has happened, there's nothing you can do from inside of Postgres to secure this scenario. You can put all sorts of super advanced encryptions and authentications inside Postgres, but if somebody else owns the operating system, they can just track exactly what you're doing and turn it into no-ops. Or just read your encryption keys and then decrypt the data right away. It's trivial to do once you reach that point. And you can sort of move up the stack with those considerations as well. Because if somebody owns your server, they will own your operating system. So it's a matter of a trust boundary, right? If you put your server in your own data center, then you have control over it. Ish. Who has access to your data center? Different story. But if you put it in a co-location, then hopefully you have a commercial agreement saying that they're not going to hack your server, but from a technical standpoint, they can. So that's how we define that. So whoever owns the server can own the operating system. Whoever owns the data center can own the server. And that goes at sort of every scale. And if you can't trust those layers, there's really nothing you can do at the Postgres layer. If you're using the cloud vendors, you can build reasonably secure solutions on Amazon Cloud, for example. But they all assume that you fully trust Amazon. Right? Amazon can do whatever they want with your data if you put it there. Now you have a commercial agreement, hopefully, that says they're not going to do that. Or same thing if you're co-locating, if you're outsourcing to somebody else, if you're outsourcing to someone who maintains your operating system and you run the database. There is hopefully something in your contract that says they can do whatever they want with your data. But from a technical perspective, they can. So there's nothing we can really do at the Postgres level. Now once we have reasonable trust or security at these layers, then we can start doing interesting things in Postgres. So we need to define our trust levels at the lowest level. So who do I trust and why? You can, in a lot of cases, probably argue that, yes, you outsource it to a professional data center somewhere, now they can hack your server. But it's probably still more secure than keeping the server under your desk. Because they have physical security, they have logs, they have cameras for who gets into the data center. But if you had your own data center with all those things, then maybe you would be more secure. So it's about picking the levels. But once you have your server in an environment that's sort of secure enough for you, the first thing that runs on your server is obviously your operating system. Now Postgres doesn't particularly care which operating system you're in for any perspective really. Whether it's from a performance perspective or a functionality perspective or a security perspective. Almost all security features in Postgres exist regardless of which operating system you use. There are a few exceptions. For example, we have an integration with Ssl Linux, which you can probably tell from the name, really only works if you have Ssl Linux, which only works on Linux. But basic things like SSL encryption or just login methods and those things are across all operating systems. So from a security perspective, probably the single most important thing to consider in operating system is pick the one that you know. If your entire business is Red Hat, don't put your Postgres on FreeBSD or even on Debian. Right? If your entire business is Windows, then maybe it actually makes sense to put Postgres on Windows as well. From a security perspective. Now Windows is one of the few exceptions where we actually say you don't get the same level of scalability and performance side of Postgres as you do on a Unix-based operating system, because Postgres is designed for the Unix-based systems. But from a security perspective, if you're going to put like 1 or 2 Linux boxes in a Windows environment, you probably don't have the skills in your organization to properly secure it. It's better to keep the things that you actually know. Now, obviously, it needs to be a supported operating system on Postgres. Don't make up your own. You can run your own, but don't do that. Same thing with distributions when you're talking about Linux. It doesn't matter whether you use, Red Hat or Debian or Ubuntu or Gentoo or Mint or whatever. Use whatever your operations people know how to use, because otherwise they will do something wrong. They might still do something wrong, but at least this way they get a chance, right? And then look at securing the operating system itself at a reasonable level. Now the thing is, you typically for a database server don't need to lock down your operating system really hard, as long as you subscribe to rule number 1, which is nobody gets to log into your server. As long as you don't have any untrusted users, only the DBAs and sysadmins can get a login to the server itself. You don't need to lock it down that hard. You should obviously still not run random services or your gaming servers, Bitcoin mining and things belong on other machines. Keep your machines dedicated to Postgres with no other login users, and it becomes pretty easily secure. In fact, most of your Unix-based systems will just come in a good configuration by default if you do that. But a classic mistake is having users that just get permissioned across every server in your entire organization because that was easier. And then one of those gets compromised and they have access to everything. You'll still want to secure things internally, like make sure that only the Postgres user has access to the Postgres data directory, because nobody else ever has any reason to do that. But keep it at a sort of reasonable level. The other thing about choosing at the operating system level is use the standard Postgres installers. It makes, for one thing, it makes your life a lot easier. Postgres is open source. You can absolutely build from source. But typically for your production environments, you don't want to be doing that. It doesn't add anything. If you need to make changes, my suggestion is if you're on a Linux-based system, say you're on Red Hat, if you need to make a modified version of Postgres with something, grab the build scripts for the Postgres RPMs and build your own using the same recipes. Same thing goes for other platforms. Because these are adapted by the packagers who know their platforms really well and set up to work the right way on that platform. So for example, if you're using the RPMs built on a Red Hat, the Ssl Linux flags will be correct. It will know about that. It will know where to find the correct version of the SSL libraries. Things like that. A classic problem I've seen with people who roll their own is then they end up with, for example, the SSL libraries, the OpenSSL. One or two of you may have heard there's been like a bug or two in OpenSSL recently. And they're still out there, right? Because people have an embedded version of it sitting around in a directory somewhere. But not even an embedded, they don't even know it's there. But their server is using it. If you're using the standard packaging, the standard installers, then you're going to end up using the standard version of all these shared security libraries. And you only have to patch once. It also gives you consistent security. You don't end up with random users. I've seen interesting scenarios where people installed the RPMs, they created a Postgres user, and then they built it manually, and they decided they needed another Postgres user for that, and then they created another Postgres user who happened to have write permissions on its own binaries and things like that, because it just became unnecessarily complicated. Stick to the standard installers and you will get the consistent security model. Same thing, which goes also the same for convenience level. If you're on a platform that has proper packages like RPMs or devs or ports or whatever, use those. There is, for example, there's a one-click graphical installer that runs on Linux as well that you can get from the Postgres website. But if you're on a Linux platform that has the packages, there is no reason at all to use those one-clicks. They do ship with libraries in them. That means you're going to have to patch them independently of your operating system. And you're giving up a lot of the advantage that you get from being on one of these operating systems in the first place. And the final part, the second final part about the operating system side is don't forget to actually keep it updated. Right? This goes for both the operating system and Postgres. Unfortunately, I think most people never patch their Postgres servers. It seems like that. Whether it's for Postgres bugs, general bugs, or Postgres security bugs, you need it patched, right? But same thing for OpenSSL. I've happily stood up and given us great examples of why you need to be updated. But this goes for other things. There have been security problems in the XML libraries that Postgres links to. There are security problems in libc. Right? We use libc. We use all these libraries. Make sure that you keep updated. Using something like Yum or apt or whatever your platform package makes that a lot easier than just manually rerunning the installation or rebuilding from source every single time. But you still have to actually do it. Just because you have Yum doesn't mean it's magically going to patch things, you have to run it. There are good monitors out there for most of these packaging systems. If you use something like Nagios or so for your monitoring, you can get an alert saying, hey, there are security patches missing on this machine. If you don't have those monitors today, you should probably install them. They're really easy to do. You can run them like once a day or something. It'll keep you known. And a classic problem on Unix, which is dealing with restarts. I mean, we all know from the good old Windows days, right? Whenever you touch something, you have to reboot. Oh, update something, reboot. Apply a patch, reboot. Now, the fact you don't have to do that on Unix, but that doesn't mean you shouldn't do that. Because if you replace, for example, libc with a security patch, you have to restart every single daemon process on your system before that patch is in effect. Because the existing processes will use the version of the file that was there when they started. It's a very common thing to think that you can just do something like apt-get upgrade and then you're patched. But it really depends on what package it was. If it happens to be the kernel, then you have to reboot. Right? Unless you're doing one of these fancy live kernel patching things that we can look into doing now. But for most people, you really don't need that. You can just reboot. Schedule it for a good time. And the same thing for the restarting services. Let me get this right. I can never keep these two apart. One of the two, whether it's the Yum or the apt. I think the apt version, if you actually patch Postgres, it will automatically restart the database server. Whereas the RPM will not. It will require you to do it. But on Debian as well, if you patch OpenSSL, it won't restart Postgres. It'll only restart whatever services OpenSSL itself might have, which is, none. Again, there are good monitors out there that you can plug in. There are monitors for Nagios, there are monitors for other systems that will fire an alert when there is a running process that is using an old version of a patched library. And that's a really good thing to monitor. In my experience, almost every single time you get like a security patch coming out from Red Hat or Debian or these sort of server level, their server versions of the distributions, almost every single time there is a couple of daemon processes that needs to be restarted. Sometimes it's Postgres, sometimes it's SSH, sometimes it's your name service cache, but there's almost always something that needs to be restarted. So keep a lookout at that. You might think that you're patched, but you're not. And these are really simple things. Now there are a few other things. One thing that people keep asking me a lot when I talk about these security things is, what about encrypting my hard drives? Does Postgres work with encrypted hard drives? And the answer is yes. Postgres works with encrypted hard drives. You encrypt it at the file system or at the storage level. Right? You can use LUKS in Postgres. Presumably you should be able to use the new ext4 encryption. It's really new. It landed in the kernel just a few weeks ago, I think, so I haven't tried it, but it should work. As long as the file system still respects the POSIX APIs, that when we write something, it gets written to disk. When we synchronize something, it gets synchronized to disk. Then it will just work. It's completely transparent to Postgres, other than that things will be slower. And potentially, if you do get disk corruption, it will be much, much harder to do anything with it, because it will be really hard to differentiate between proper data that's been encrypted and corrupt data that's been encrypted, because they all look corrupt once you look at them. But as long as that doesn't happen, then yes, it works, and it works fine. The question you have to ask yourself with that is, what's the attack vector? What are you actually protecting against, and where did you put the keys? If you put the keys on the server so that it can boot, then you added nothing. Right? What did you really help? The keys are right there. If someone breaks in and steals your server and runs off with it, well, you put the keys on the server. So they stole the keys by default. And that's really, encrypted disks only protect you against someone physically stealing and running off with your disks. Right? If the server is running, then the disks are unencrypted at the time. Key management will, if you use things like locks, you can put your encryption key on a USB stick, for example. That works as long as you don't leave the USB stick in the server. Because if they steal the server and the USB stick is in it, they probably stole the USB stick without even thinking about it. But if you take the USB stick out and put it in a safe every time, then it does actually improve, because if an offline attack against your server just now requires breaking what's hopefully a strong encryption. Of course, you also broke your own ability to reboot the server without being there physically. Because if you reboot, it doesn't come back up until you put the USB stick in. So that's just something to consider. It sounds really good to encrypt your hard drives, but for something like a database server, it seldom makes any sense. Now we also see a lot of use cases where we have Postgres running as a desktop database or embedded database underneath some sort of a desktop application on a laptop, for example. Now it makes a lot more sense to do disk encryption, because a laptop more or less will get stolen. It's really easy for that to happen. And there will always be somebody present when it boots up, so you can just input the password. So full disk encryption on the laptop makes a lot more sense than it does on your actual database server. Unfortunately, I've come across more than once scenarios where there is basically a requirement, there is a regulatory requirement from the government, if you want to store this type of data, you must encrypt your disks. And it doesn't actually matter what you do with the keys. So it's completely pointless encryption, but it has to be 128-bit, so that it's not too fast. And look, it doesn't add security, but it fulfills the requirements of the authorities, which sometimes can be a feature in its own. One more thing to consider on the operating system is really multi-instances. If you're running more than one Postgres on the same server. If you run them just by the way that things will run by default, which is they'll all run as the same server, if you use PG create cluster, for example, on Debian, to create a second cluster on the same machine, they will run as the same operating system user. Same thing if you create multiple versions on Red Hat systems, for example, they'll all run as the user Postgres, which means they're running in the same security domain. It's very simple to add sort of one layer of security, at least, by running each instance as a different user. Postgres and maybe Postgres 2, or something else, but run them as different users. That'll give you reasonable level of separation. If they run as the same user, then anyone who has, say, super user access in one instance can do whatever he wants with the other instance. And that was probably not what you intended. You thought that these were fully isolated. They are almost fully isolated as long as you never use a super user. But if you use a super user, they're not isolated at all. He can do whatever he wants in the other instance. And given the price, performance-wise, that we have today of things like containers or virtualization, if you actually need them to be in separate security domains, it probably makes sense to use virtualization or a container or a C group or something to cut them apart properly. There is a little bit of overhead, but if you need all that performance, you probably shouldn't be using multi-instance in the first place, because they're competing for the same resources anyway, even to begin with. So while virtualization adds a little bit of overhead, from a security perspective, it makes it a lot harder. Because breaking out of one virtualized container and into another one, that is really supposed to be hard. If that's easy, you need another virtualization engine, or you forgot to apply a patch, or restart patching. So that's a good start. Operating system, that's the easy part, right? It's not really Postgres specific. If you need to secure your operating system properly and you don't feel you know how to do that, there are people out there who know how to do that. Hopefully they're in your organization. Postgres doesn't make any security requirements on your operating system that's not fulfilled by any of the normal standard versions of operating systems today. And it does not require you to unlock or to remove any sort of level of security from your operating system. So make sure that you secure that part as much as you can. And of course, then again, as you go further up the stack, make sure you have whatever hardware or data center level security is something that's appropriate for your organization. Now, getting into a few of the things that are a little bit more Postgres specific, things that we do in Postgres. If we look at communications security, securing a Postgres communications channel is reasonably easy. But again, where do you start? Do you need to do that? Is there an attack vector against your actual communications? In the case, I mean, a classic case is, well, what if my web server is sitting, at the top of the rack and the database server is sitting at the bottom of the rack, and they have a crossover cable? What's the actual attack vectors that are reasonable to see against this? I mean, if someone has broken into your data center, they might just take the server and run off with it instead. They're more likely to get away with that. But if your database server is in one cloud provider and your app server is in a different cloud provider, how many potential attack vectors are there against the communications between those? That's a lot more. All ways, or I'd say almost all the ways of securing communications will come with some level of overhead. And again, it comes back to figuring out whether you're willing to pay that overhead or not. And this is, again, you go stack down to up, right? If you can secure things by physical security, that's awesome. Like, nobody gets in, but it's as they say, the securest computer is, what is it, in like a concrete block at the bottom of the ocean or something like that. It's not very useful. Usually you want to be able to somehow communicate, but I mean, I have some clients who actually have their, part of their Postgres security is entirely based on physical security. And their physical security includes things like there are no computers within 300 meters of the fence because, electromagnetic radiation might leak. Okay, most of you probably don't have that requirement or even the ability to do so. But if that works for them, that means they don't encrypt that data. And going up with things like firewalls, I'm sure you've heard of the concept, maybe even seen one. We have VPNs, we have IPsec, we have SSL, we have all these different ways that we can lock down and secure the communications between a Postgres client and a Postgres server. Now, Postgres traffic in a firewall is actually really simple. It's a single port TCP. Unlike someone who's once tried to properly secure SQL Server traffic, back in the days when they used RPC, that was no fun. Postgres is single port TCP. The default port is 5432, as I'm sure you're aware. If you change the port, it's still a single port. That's all there is to it. In almost every case, this port should, of course, be blocked at the perimeter. Right? You have a network firewall before you get to the internet. You should not let Postgres through that pretty much ever. If you actually have clients on the internet who need to talk directly to Postgres, you want to implement something like a VPN or something to get through the firewall. You don't want random IP addresses connecting directly to your Postgres port. Even if Postgres isn't going to let them log in, it's still a lot of overhead in just figuring out that they're not allowed to log in, that you can block much cheaper in a firewall. And we have actually, I think once at least, had a security vulnerability in Postgres where you could do bad things without logging in first. Where you could do bad things before the Postgres protection kicked in. So there's no reason not to block that. And we can obviously block port 5432 in a host-based firewall as well. I mean, every Linux or BSD or whatever Unix box will have some version of an IP filter on the host. So block them there as well. Postgres by default will only bind to the localhost interface, so 127.0.0.1 or ::1 if you're on v6. But I'd still say it's a good idea to explicitly block 5432 on that machine, or just to explicitly block everything except whatever you want to let in. Because sometime in the future, somebody's going to go in there and reconfigure the Postgres to suddenly listen to something, and then you want it to still be blocked in the firewall. So having a firewall is important, but having a firewall does not replace using the PG HBA file. So I'm sure, who's ever used a PGHBA file to configure their system? Well, the rest of you should be using PGHBA file to configure your system, right? It's the, I'm going to go into more detail about that one later, but it's sort of the firewall that's built into Postgres, right? But a firewall that runs at the network layer or at the host layer can block attacks much cheaper than Postgres can do. Because Postgres has to go through a number of steps before it realizes it. The firewall would just look at the source IP and go like, I don't know who this is, he's out of here. So that's all pretty simple. Now if you actually need access from outside of your trusted network, and that may not be your whole corporate network, it may be just the network that has your database server in it, or a few database servers, or other sensitive resources. VPN is obviously a solution. Again, since Postgres runs on a single TCP stream, it'll run over any type of VPN that you can think of, whether it's a site-to-site or a host-to-site. Or I've seen a fair number of cases using just a host-to-host VPN. So basically you run a VPN service on your database server that roaming clients can connect to, and authenticate to the VPN, and then open a tunnel through the VPN back into the same server. It all works exactly the same, and Postgres doesn't care. As long as you have IP routing for a single TCP stream working across your VPN, Postgres works across your VPN. It's that simple. And obviously, there's no real point in doing it again if you don't also do a firewall. But usually they come in the same package, right? So these are good ways of securing like tunnel mode. Has anyone ever deployed IPsec in transport security mode? No one? Okay. One? Maybe. It's actually, I found it's a really convenient thing to do if you can manage to get the infrastructure up and running. But IPsec, I'm sure many of you, most of you have probably used IPsec in the form of a VPN, like an IPsec-based VPN. Now, transport level IPsec basically sets up encryption keys between the machines, but no tunnel. And every IP package, well, according to matching rules, but IP packages between the machines are just encrypted at a kernel level before you see them. So there are good tools, there are ways of doing very, very detailed security policies and encryption policies. This is something that typically works well only within your network, within your LAN. But if you do that, you can basically get every single IP package within your LAN to be automatically and fully transparently encrypted and authenticated. Yeah, there's a bit of overhead to that, but now your network is actually secure. Right? Anyone who manages to even dump all the network traffic, if they hack into one of your core switches and dumps the traffic, they get nothing. It's all encrypted data. It can be kind of a trick to set up. I've tried and failed to set that up on Linux once. I've only tried it once myself. I know people who've made it work, and I've made Postgres work in their networks, so I know that works. I have managed to actually, back in older days, get that properly set up in a Windows environment, where it turns out it was much easier because of, there are a few things with the Active Directory that makes that really easy. But it's something to consider for local connections. You can also just specifically configure IPsec policies on your database server. For example, saying, if the other end does not have an authenticated IPsec session, I don't exist. And it'll just drop every other package on the floor, and you'll never see it. So these are ways to really enhance the network security at a layer that's independent of Postgres. One advantage being, of course, now you're also securing everything else that you might happen to have on this machine. If we look Postgres specific, the only thing that we provide today is SSL or TLS, or whichever you want to call it, which is a connection encryption on an individual connection. I'm pretty sure you all know the general concept of SSL. You may have seen like a secure website in your browser. It's the same thing. SSL is a wrapper that can run around multiple protocols. In Postgres, the standard Postgres protocol has been adapted with a mode. It has a negotiation, and then it will just apply standard SSL wrapping to all the contents. But it's slightly protocol adapted, so it's not, for example, like HTTPS, which is just a completely separate embedded connection on a different port. Postgres will speak SSL internally in its connection. Now the implementation that we have in SSL in Postgres today is OpenSSL only. The good thing about that is OpenSSL has gotten a lot better from a security perspective in just the last year because of all these high-profile attacks. We can be naive and say, hey, OpenSSL has all the bugs, we should use something else. But it might also be that the bugs in the other products just haven't been found yet. So the good thing about all the things we've had with OpenSSL is there is a lot of good people now who are actively working to make OpenSSL better. Now there's work done in Postgres as well to make us not dependent on just OpenSSL. In fact, the upcoming Postgres 9.5 has a hopefully complete abstraction of the SSL provider library so that we can have more than one SSL provider. We don't actually ship with another provider at this point, but it's groundwork for future. One of the main reasons for that is that we'd like to integrate, if you use Postgres, whether it's the client or the server, on Windows. We'd like to use the Windows SSL providers instead of bringing in our own. Because again, we're bringing in OpenSSL as an embedded thing. That means that the Postgres installation is now in charge of patching OpenSSL, for example. But if we could use the Windows implementation, then that would all be Microsoft's problem. And we'd be able to use certificates and things as set up in your Windows environment, which we don't today. So we're hoping to get there. We're not there just yet. We have the abstraction, and hopefully it's at the right layer. Now, like any other SSL service, Postgres will require a certificate, and it will require a private key. SSL is always based on RSA, DSA, public key encryption, with a negotiation back and forth between the client and server. You can't make an SSL connection without a server key and a server certificate. You can make it with or without a client key and a client certificate. Those are optional. But on the server side, they're not optional. So we need that, again, as does every other SSL service that's out there. Now, by default in a Postgres installation, SSL is disabled on the server and enabled on the client. The one big exception I know is if you're on Linux and you're on a Debian-derived system, they've changed the default to enable SSL on the server as well. But a standard Postgres has SSL disabled by default because the assumption is if you haven't actually set anything up, then you probably don't want to pay the overhead of doing SSL on everything. But it's not particularly hard to set it up and to actually get it running for Postgres. Now the actual SSL is negotiated upon connection. So the very first thing that happens when a Postgres client connects to a Postgres server is a negotiation about SSL. It runs on the same port. So it's not like HTTP, where you have port 80 is clear text and port 443 is HTTPS by default. But it all runs on the same port. In that way, it's more like SMTP, which runs on port 25, and then you can run the start TLS command and get encryption. Postgres is actually very simple. It's see if I get this right in the order. Client connects to the server sends a single byte back to the client, telling it whether it has SSL support or not. And then the client decides whether to send a package back saying whether it has and wants to use SSL or not. And at that point, if they agreed on using SSL, then from the next byte on, everything will be encrypted within the SSL tunnel. So the first thing that happens there is the actual low-level SSL negotiation, which Postgres doesn't do API-wise anything with. It just tells OpenSSL to give me an encrypted connection now on this socket here. So it happens before any level of authentication and anything like that, which means that if we're using SSL, we can easily use things like passwords in clear text, because it's only clear text before it enters into the SSL tunnel, then it's fully encrypted all the way across. So it happens before pretty much everything. It's only IPsec that can potentially happen even earlier, because you will have, before you've been able to authenticate the client, you will know the IP address of the client and the server. Whereas something like IPsec can actually drop the packets before you even know that there is a Postgres server existing. But we have to have a Postgres server at this point. Now on the certificate side, as we said, a server certificate is mandatory. You cannot get SSL up and working without having a server certificate. It does not need to use a public CA. In fact, in almost every case, it shouldn't use a public CA. So you shouldn't run off to whoever sells you the web browser certificates and say, hey, I want a certificate for my database server. The reason that we need to do that for our web server is that we have browsers connecting who are not under our control. We have visitors from the internet, probably. And the CA acts as an intermediary saying, hey, I promise that this server over here is who it claims to be. You probably, I should say hopefully, don't have random Postgres clients on the internet from untrusted people connecting directly to your database server. If you have that, then it makes sense to use a public CA. If you don't have that, it does not make any sense to use a public CA. It'll only cost you money and decrease your flexibility. Now Postgres works fine with what you call a snake oil self-signed certificate, where the certificate is its own CA. So CA is the certificate authority that says who the server is. And if the server, so basically the CA certificate signs the server's certificate with a digital signature saying, I know who this server is and it's okay. And if the server just signs itself saying, I know who I am and you can trust me on that, Postgres will work fine. You will get encryption on your connections. It does not give you protection against what is known as man-in-the-middle attacks, because somebody else could just do the same thing. And if your client accidentally connects to the wrong server, it'll not know the better because it claims that's who it is. But if you know that that can happen for other reasons, if you don't care about that for other reasons, then using one of these self-signed snake oil certs will work. It'll work perfectly fine. What you probably want to do if you're deploying any larger scale SSL for Postgres is to use a custom, potentially a dedicated CA, just for your Postgres installation. If your system or if your organization already has an enterprise CA of some kind that you already use to hand out other certificates within your organization, you can obviously use that. Perfectly fine. If you don't have it, OpenSSL, for example, lets you create a simple CA that will make it work for you. It's not as user-friendly as some of the other ones you can, buy from someone, or there are packages you can get that are open source that almost work, but it works. Actually doing a CA is not that complicated. The hard thing about handling a certificate authority is keeping the actual CA secure. Because if someone breaks into that, they broke everything. Right? They can now issue certificates in the wrong names, which takes out the whole point of this. So as we said, OpenSSL comes with a built-in CA. Go ahead and use it, or use something else. There are many out there. Postgres doesn't require you to distribute the CA certificate. A Postgres client doesn't actually need to know which CA issued the certificate for the server. But again, if it doesn't, it can't protect you against a man-in-the-middle attack. So as a general rule, you should have a system in place for distributing your CA certificate to all your nodes, because they will then use that CA certificate and say, okay, I trust whoever this CA trusts. And then that CA says, well, I trust this Postgres server over here. And now you have established the trust relationship as required. What you should not do, which surprisingly many people do, is you should not distribute the key to the CA to every node. Because if you have the key to the CA, then you can just do whatever you want. The key to the CA is the most secure or security sensitive part of your CA installation. Don't go copying that everywhere. Now OpenSSL, for example, will put them in the same directory by default. So be a little bit careful about that. Or whichever CA you're using, make sure it works that way. So setting up the server-side security on Postgres is very straightforward. Again, it's very similar to how you would set it up for any other SSL service, like a web server. You generate a secret key and a public key. Based on these, you generate what is known as a certificate request. It's a very nice markup error down there. And then you sign that request. The signing happens at the CA. And then you deploy this certificate that you get back from the CA. So looking at a couple of quick examples of how we do this specifically with OpenSSL. Now, just because Postgres uses OpenSSL doesn't mean you have to generate your certificates using OpenSSL. There's a standard format. Postgres uses a PEM format standard for certificates. You can generate it with whatever tool you want, but OpenSSL comes with a way of doing it. So in this case, we're saying OpenSSL rec, which is I want to create a certificate request. I want to create a new key. In this case, I'm creating a 4096-bit RSA key. Defaults in way too many OpenSSLs are still 1024. I think the powers that we have determined that that's a bad idea by now, and that you should be using bigger keys than 1024, just to be a little bit forward. And then we just say, write the output in text format to server.rec. Any sort of general SSL parameters apply. It will take your default OpenSSL configuration and apply those. You can change that. As with most services, you should always set the CN, or the common name field, because OpenSSL here will prompt you for a number of things, like which city and country you're in, things like that. It prompts you for a common name. The common name should always be set to the server name. So if your server is database1.company.com, the CN should be set to database1.company.com, so that we can full verification on it. That's the only attribute in the certificate that Postgres actually uses. All these things that you can set about country and city and location, things like that, Postgres will never use those. Now there might be a Postgres client that might in some way display it to the user. I don't actually know of one, but there could be. But Postgres doesn't use it. It only looks at the CN and the fact that it's signed the right way. Now it doesn't have to be an RSA key. If you prefer using the other, like DSA or Ldap Url and all those things. As long as OpenSSL can do it, then Postgres can do it. We don't do any of that ourselves. It's all in OpenSSL. Now one somewhat annoying thing about this is OpenSSL will also prompt you for a password. And you have to lock the private key with this password. The problem is that a private key with a password means that Postgres can't start, because it needs the password. Now in OpenSSL, you can get rid of the password, you just have to run a separate command for it. So basically, what you run is the command OpenSSL RSA, because this is an RSA key, read privkey.pem, and write it out to server.key. If you don't say anything else, that thing is going to prompt you for the password to read it, and then it's going to write it out without a password. So on the OpenSSL rec, the default is to add a password. On the OpenSSL RSA, the default is not to add a password. Nobody ever said they were consistent. So you need to do that in order for Postgres to start properly. Now once you've done this, you store this server.key in a secure way. Because if anyone gets to that server.key, they can compromise your server. They can compromise all the security. Now Postgres wants this in the data directory. So you can create it there in the first place, you can create it somewhere else. It should be readable only by the Postgres user, and nobody else. And then you somehow transfer this .rec file, the certificate request, to your CA. This doesn't actually have to be very secure. This file in itself is not that sensitive. If you verify the fingerprint when it gets to the other end. Because if someone can modify it in flight, you have a problem. So get it over to the CA, and then we have the CA sign this request. If you happen to have an OpenSSL CA, use that. If you don't have a CA, you can do one of these self-signed certs. which is done like this. You say OpenSSL, you do the request. X509 is the format that we use for certificates or the protocol. You just read in the server request. You use the server.key to sign it and write the certificate to server.crt. Now that will generate one of these snake oil certificates that is really only trusted if you copy the certificate everywhere, which takes part of the point away. But you will get something that's basic and that works. If you're using a separate OpenSSL CA, then you just need to use a different server.key, the one that comes from the CA, so that you use the CA's encryption key to sign the certificate request that came from the server. And this will generate your server certificate, which you transfer back to your database server in a secure way. So again, if someone can modify this, or if they can steal this, then you might have a problem. You need the server to be securely transferred and stuck in the data directory of your server. Now once you've done that, you have enough to get going on the server side. And if you're dealing with snake oil self-signed certificates, you have enough. You can start working. Right? But as we said, what you really want is you want the CA certificate to be distributed. And since Postgres runs the way it doesn't integrate with, even if you're on Windows, it doesn't use the Windows Cert Store, it doesn't use the GNOME Certificate Store, which I think there is one, or anything like that. So for each client, it will need the CA certificate. This is not the key, just the certificate from the CA. It's not required, but if you don't have it, then you can't do validation. And it's highly recommended that you actually do validation if you're doing SSL. So the default for Postgres is you want that in your home directory.PostgreSQL and called root.crt. That's the default location you want it in on every client for every user. Now you can change the location of that file through a connection parameter. You can say I want to connect, but for this connection my root CA certificate is over here. And you can set an environment variable that will change it, PG_SSL root file or something like that. That will tell you for everyone on this machine, for example, the certificate is somewhere else. But that's where it needs to go. If your CA uses a CRL, a certificate revocation list, which is basically the CA publishes a list of which certificates that it issued before should no longer be trusted. For example, because someone stole it. Then you need to distribute that as well. Postgres doesn't synchronize that somehow down through the server or anything. And that one goes in the same directory. It's just called root.crl instead of CRT. And again, this one can also be changed on the connection string or in an environment variable to make it pick it from somewhere else. If the CRL doesn't exist, Postgres will just not check CRLs. If the CRT doesn't exist, Postgres will not do any validation of the server certificate, which again, you probably want. Now once you have that out on your client, you can enable SSL on your server. Set the parameter SSL to on, say postgres.conf. And make sure that you have the server.key and server.crt in your data directory. So again, there are config parameters in postgres.conf if you want to put them somewhere else. Wherever you put them, check permissions. They should be owned by Postgres, and then should be mode 0600. I don't think we actually validate that it's 0600, but we validate that the two last bits are 0, that nobody else has permissions, but it could be another combination of something 0, something 0, 0. And once you've done that, you need to restart. You can't reload. It requires a full restart of Postgres to make it, load the SSL negotiation code. In fact, Postgres, as it is today, if you want to change your certificate, you also have to restart. I know there is a patch actually sitting on the current commit fest for 9.6 to make it possible to change certificate without a full restart. But right now, you have to do that. So you assign your certificates an expiry time. When they expire, you have to restart Postgres. So that's probably something to, don't forget to put it on your calendar when you install the certificate. It's going to expire a year from now, or 2 years from now, or whatever you happen to set up. So once you've done that, Postgres will actually be ready to run, and anyone who connects to Postgres at this point will get encryption. If they have the root certificate, they will get validation and encryption, because that's the default of the client. Remember, the server has SSL disabled by default, but the client has SSL enabled by default. So in these cases, it'll just start using SSL. If you want to use client certificates, you must put the CA certificate on the client, on the server as well. Now, it doesn't hurt to do that, even if your client, if you're not using client certificates for login. Same thing for a CRL. It's not required, but if you are using client certificates for authentication or for just requiring client certificates, it is recommended that you have a CRL. Otherwise, you have no way, if someone steals one of your clients, they ran off with a certificate, and you can't block it in any way. So you'll want the ability to put the CRL there. Same as with the certificates, by default, they go in the data directory, wherever that happens to be. But you have configuration parameters in postgres.conf that you can change them to point them to sort of wherever you want. Now SSL, as I mentioned, it's negotiated between the client and the server immediately upon connection. So basically what happens is the server provides SSL, or it doesn't provide SSL. That's the first package that goes back saying, I can do SSL if you want. Or, I don't know what SSL is, I can't do it. Those are the two potential answers. And then the client makes the decision of making an SSL connection or not making an SSL connection. And this behavior is controlled by the Ssl Mode parameter. That's a libpq connection parameter. It can also be setting it through an environment variable. You can put it in your services file, and it'll use those. Now the default SSL mode in Postgres is preferred. There are a number of different modes. There are 5 different modes that we can use. And prefer is potentially the stupidest one of them all. Unfortunately, it's the default. What SSL mode prefer, and the default behavior of the Postgres client is when the client connects, if the server supports SSL, the connection will be encrypted. If the server does not support SSL, the connection will not be encrypted. So the client doesn't know. And there is nowhere for the client or the client application to make any decision until after it has, for example, sent its password, potentially in clear text. If you're actually deploying SSL, this default makes sense as long as you're not using SSL, right? But if you're actually using SSL, you should, in pretty much every single case, override the value of SSL mode, because the default is kind of silly. For those of you who've seen me do these talks before, you've seen this table before. Have you seen this table before, Bruce? Once or twice or 3 times? I made it many years ago to try to prove how stupid the default is.
It's got a new column.
Sorry? It's got a new column?
Your performance is new, that column.
Yeah, it's only like 5 years. Okay, so basically the idea here is, these are the different modes that we support. We can say disable, allow, prefer, require, verify CA, and verify full. Then we got 2 here. Does this protect us against eavesdropping? And the thing with security is it only protects you if it actually guarantees you that it protects you, right? If it says, maybe I will encrypt your data, then the fact is it doesn't protect you. Because if someone wants to attack you, they'll just attack the pre-negotiation package saying, oh, the server doesn't support SSL, and now everything goes in clear text. And the second one, does it protect you against the man-in-the-middle attack? That means, can somebody else go in there? Do you know that you're talking to the correct server? Or might you be sending your login credentials to somebody completely different? These are the 2 scenarios that we try to protect with SSL. And the next two columns here are SSL required and SSL disabled. That corresponds to how those things are on the server. If my server is configured to require SSL, what will happen? If my server is configured to without support for SSL, what will happen? Now, if you look from the bottom, it probably says itself, like client mode equals disabled means the client just doesn't do SSL. If your client is built without support for SSL, that will be the default, obviously. But you can also set this in the SSL mode. You can say, I want to make this connection, and I don't want it to be encrypted. In that case, rather obviously, you don't get protection against anything, because you just turn it off. If the SSL is required on the server, the connection will fail. Because you just said, I don't want to do SSL. And then you said, but it's required. Whereas if SSL is disabled, obviously it works. And there's no overhead because we're not encrypting anything. That one's pretty straightforward. SSL mode allow, which is the one that I've argued should probably be the default and failed, means allow means if the client connects and the server supports SSL but doesn't require it, we won't do encryption. But if the server requires encryption, then we will do it. Obviously, this does not protect us against eavesdropping or man-in-the-middle attacks, because if we're connecting to a server that doesn't do SSL, it becomes clear text. But it works whether SSL is required or not. It'll just, choose unencrypted if possible, which means that we choose from the client side to say, I'll pay the overhead of encryption if I have to. But I won't pay it unless I really have to. So I'll try to go unencrypted. Prefer, being the default one, says if the server supports SSL, it'll be encrypted. If the server doesn't support SSL, it'll be in clear text. Meaning it doesn't actually protect you against eavesdropping or man-in-the-middle because you don't know if the server does encryption. If there is someone who attacks the connection in the middle, they'll just say, this is an unencrypted connection, and you're fine with it. It will work whether SSL is required or not. And basically what you're saying is, I'd like to be given the chance to please pay the overhead of encryption, but I'd rather not get any of the security from it. Which is kind of silly, but it's the default. Now if you are using SSL because you actually care about the security, you want to be used one of the three remaining options. Require, verify CA, or verify full. Require just means if the server doesn't speak SSL, you're not going to connect. But it doesn't do any validation of the certificate. So this is the one that works if you use a snake oil certificate. Because we can't validate the certificate, but in mode require, we don't care. So we do get eavesdropping protection. No matter what, our connection will be encrypted. We have a guarantee of that. But we don't know who we're talking to. Now, depending on our infrastructure, that's a perfectly valid situation in a lot of cases. Saying, I want the data to be encrypted, but I trust whoever's on the other side. I might have verified that in other ways. In this case, if SSL is required on the server, it works. If SSL is not supported on the server, the connection fails. Because we required SSL and there is none to be had. And we're saying, yes, I'd like to pay the performance overhead of SSL in order to get the security. But we're guaranteed to get the security. Now there are two remaining options, verify CA and verify full, are two different ways of validating who is on the other side. If we say verify CA, Postgres will verify the certificate that it gets from the server that it has been issued by a trusted certificate authority. So whoever signed the request sort of adds the trust level. Verify full will also verify that the name of the server you're trying to connect to matches the name that's on the server's certificate. So if the certificate was made for database1.company.com and I try to connect to it as database1.company.com, it works. But if I try to connect to it maybe just as database1 without the domain name, it fails. If I try to connect it as database4, it fails. If I try to connect with the raw IP address and not the host name, it fails. This is what you'll typically see in your web browser, right? When you get the name of the certificate, the site doesn't match the name of the server. But Postgres doesn't have the ability to do what we did. Like the web browser will give you a pop-up or screen that says you can bypass it. There's no interface to do that in Postgres. So if that happens, it'll just fail. Now these are both valid ways of doing it, of course. They both protect you against eavesdropping and man in the middle. The verify full basically protects you against a scenario where you're being attacked by somebody else who was trusted by the same CA. Which, if it's your own internal CA, that should never happen. Really, it should never happen. Don't issue certificates to attackers. That's generally a bad idea. But if the certificate is issued by some random CA on the internet, it's good to double verify. I'd say most of the cases where verify full actually ends up blocking, I've seen it do that, it's been because of a misconfiguration somewhere. Because of this, yeah, you're accidentally accessing it as database 1 instead of as database1.company.com, and it'll break. So in most cases, I'll say verify CA is probably the right choice if you're deploying this on an internal application. You trust the CA, you issue your own certificates, and then you just tell Postgres that whoever the CA trusted, I'm fine, I'm trusting that one too. Yes? Do we have a microphone? Yes, microphone is on its way.
Does Postgres checks revocation lists?
Does Postgres check a revocation list? Yes, it does if you have put it there. So, if I go back here, sorry, wrong screen, here. The client will check the revocation list if you have a CRL file in the .postgres directory. But it's up to you to make sure the CRL file actually ends up there. If it isn't there, it will not be checked. Yes, someone there?
I have two questions. First one, I have two not self-rated certificate, and can I install both?
On one instance of the Postgres server can only have one certificate.
Yeah.
Now, what's coming in 9.5 of Postgres is that you will be able to use the subject alternate name, so you can have more than one name. But prior to 9.5, you couldn't do that. It's just one name, one certificate.
One name, one certificate. I have 2 or 3 certificate on different name, but I want to install in one instance of Postgres. Yeah.
You can't do that. One instance has to have one certificate. That's a limitation of how SSL works. SSL has to start by presenting the certificate.
And I must install different instance of Postgres.
Yes, if you have different instances of Postgres, then you can and should use different certificates on those, one for each instance.
Okay. And the second question, that supported token for storage certificate and ghost ciphers.
Postgres will support whatever OpenSSL supports. So for example, you can, if you have an OpenSSL engine, as they call it, that supports a specific way of storage, maybe on a smart card or something like that, then Postgres will implicitly support that. That's all handled by OpenSSL for us.
Okay.
So that part should just work, assuming that it has OpenSSL support. If it doesn't, then, you know.
Thank you.
The next part about that is, as I mentioned, it's actually the client. At the protocol level, it's the client that decides whether you get encryption or not, whether you get SSL or not. So the server provides a Boolean basically saying, I can do it or not, and then the client decides. Now, usually we consider it a bad idea to let the client make security decisions, just as a general thing. So what happens here is the client decides, but the server can then just say, well, the client decided the wrong thing, so he can't log in anyway. So it's a multi-step process. The client can say, I will only speak to you if you're encrypted. What will actually happen with an unencrypted client is, at a protocol level, the server says back, I can speak SSL or not. And the client will say, well, I'm not speaking SSL. And then the server replies, well, then you can't log in. So you can enforce it from the server. But at the protocol level, that happens at one step later. So you get a different error message, basically. And you've gone through one extra round trip. One reason for this is that we control this from this PGHPA file so that we can make this parameter different depending on which IP address the client's connecting from, for example. Or depending on who the client is, what they're trying to do, whether they're already over a VPN or something like that. This is done using the host SSL line in PGHPA. So again, I'm going to show a little bit more detail about that file later, but basically, if you're using SSL, all your lines in PGHPA should really begin with host SSL. By default, again, they're saying host, which means they'll match whether it's encrypted or not. But with host SSL, you're only able to use this if it's encrypted. And if you're using, again, SSL for real, then you really should be using this. SSL also has the ability to use client certificates. It's basically exactly the same kind of certificate. You generate it the same way. You just set the little flag on it that says it's a client certificate and not a server one. That lets the server trust the client. So we use the CA validation to make sure the client can trust the server. This is also so that the server can trust the client. It is not required by default. Postgres will run without client certificates by default. But if you add the parameter client cert equals 1 into your HPA file, so again, you can do this individually for different IP addresses, saying maybe if the client comes from a different network, require a client certificate, but if it's a local client, then don't require it. Something like that. We just add client cert equals 1 to the end of the line, and now Postgres will require a signed client certificate. This needs the root CA to be in the Postgres server directory as well, obviously. And it will then trust any certificate that goes there. Now, if your client is based on libpq, and this is basically every client driver except for Java and .NET, then we'll want, what we normally want is we want the client certificate in a PEM format file, which is the same kind of file that we used on the server. But we do also support any OpenSSL compatible engine. So you can get the certificate, for example, of a smart card, if your smart card has an OpenSSL driver. If you're using the Java driver, the JDBC driver, for example, well, then you need the certificate in the format that the JVM SSL library can read and use. And if you want to use a smart card, well, you need something that comes with a Java driver, basically. And the same thing if you're using .NET, because those use their platform native SSL instead of OpenSSL. But any driver that uses OpenSSL, it's a PEM or OpenSSL engine. It gets validated against the root CA, so this is another one of those reasons why it's good to have your own CA. If you're using GeoTrust, that means you just trust in every single certificate that GeoTrust ever issued, and not just the ones that you issued, which is probably not right. And if all we do is say client cert equals 1, that means that we require the client certificate exist. We don't care what's in it. It needs to exist, and it needs to be trusted by our CA. But we don't care who owns the certificate. We just say it has to be there. The next step up is that we can also use the client certificates to do full database login. In this case, we're going to extract the username from the CN. So again, it's only the CN field that we use. The common name of the certificate is the only thing that Postgres uses. We're going to extract the username from the CN field and log you into the database as that user. again, it must still chain up to this known CA. So we validate that it's valid, we grab the username, and then we'll log you in. I can show an example of that a bit later as well. So client certs are a way to enhance sort of both the encryption level and also the authentication level. Which brings me to the next part, which is authentication. Because it doesn't really matter too much if you encrypt the connection that the attacker is using. It's much better if it's not the attacker that's using the connection. So authenticating is really about making sure that the user in the other end is who he or she claims to be, and that they can prove it. And this is where I think Postgres probably has the most flexible layer of any database I've seen in how complicated solutions you can make with this. Don't make them too complicated, by the way, so they get something wrong, but you can do a lot of things. Postgres supports a lot of different methods. And this is what we use this HBA, or host-based authentication for. And the thing where it separates from a lot of other databases is that you can use all of these different methods at the same time for different users, and for different clients. Saying, depending on where you're connecting from, you get to use different ways of authenticating into the system. You don't all have to use the same. And this is unfortunately one of those things I see a lot of people just sort of dumbing down PGHBA because they think it's a little bit too complicated and they just want to get started, so they just let everybody log in or something like that. But if you're actually building a secure installation, spend a few minutes working on this thing. You don't need to work that hard to make an environment that's actually really secure. Now PGHBA, basically it's a top-to-bottom file. It's a text file, like all Postgres config files, where for each connection, every time someone connects, we'll parse this file from top to bottom, and we'll check, does this connection match the expression that's on this line? And this expression is made of connection type, username, database name, and where the connection is coming from. So it can be, this is an SSL connection or a non-SSL connection. It can be, for user Postgres or for user Magnus. It can be connecting to a database Postgres or database web app. It can be the connection source coming from this IP, from a local IP, or from a roving client over VPN. So it's basically a combination of a firewall and a choice of authentication. Because if nothing that you put into PGHBA matches a connection that's tried to make, then that connection is just disconnected with an error message. So just to show this one real quick on how it works, this is actually a slightly stripped down version of something used by one of my clients, which I use. This is a very simple, very short file that will show a rather significant improvement of security on a default. It's a classic case of someone running a web app and they have some local DBAs and things like that. So if we start looking at the very top of it, we have a connection saying local. That means it's connecting over a Unix socket, so TCP is not even involved. Somehow connecting locally. Second column is which database is it trying to connect to. For some reason, that is just pure history. The wildcard is all. We don't use a star for that. I'm not really sure why. I'll look at you, Bruce. Do you have any idea why?
I have not a clue.
Not a clue. Okay, yeah. It's just been that way forever. It's kind of weird. That means if you actually have a database named all, you need to quote it. Yes, I've run into that. This third column, username. Again, the wildcard is all. So whatever user is trying to connect to whatever database, as long as they're connecting over a local Unix socket, then at the very end out there we say peer. It means we're going to use the authentication method peer, which means we ask the local kernel who is on the other end. The second row, we say host. That means that this row is going to match if the connection is IP. It doesn't care whether it's encrypted or not. So both encrypted and clear text connections. Again, all, any database, any user. The connection comes in from 127.0.0.1/32, so basically it's localhost. Then we say MD5, which means we're going to prompt the user for a password. Okay, so localhost connections. The reason you might need that is there are local tools. Normally you'd want to use a local connection over Unix sockets. That doesn't work if your client is Java or .NET. And it doesn't work if your server is Windows, because for some reason Unix sockets are not on Windows. It's almost in the name. You can almost guess that. Now the third row is when it starts to become a little bit more interesting. Then we say host no SSL. That means we're only going to match a clear text connection. If this is an encrypted TCP connection, it's not going to match and it's going to fall through to the next row. And then we say the user is trying to connect to the database called WebDB. And the user is claiming to be web user. And the user is connecting from the subnet 10.110/30. Hopefully that's where our web servers are. If they're not, someone did something really stupid. And then we'll say MD5 again. So we're going to prompt it for a password, which is probably stored in the web server config. And the last row in this case says host SSL, meaning it's only going to allow encrypted connections to any database. And then you see this little special syntax where it says plus admin, means the user trying to authenticate is a member of the admin role. Presumably that would be our DBAs, and not our web user. And the connection comes in from 192.168.00/24. Then we're going to use GSS API, which is a Kerberos-based login. We can go through those details in a bit. But just something sort of as simple as this, for your typical web app has actually pretty well increased the security. Because when, and we all know it's a when, right? When your web app server gets hacked, it's not if, it's when, then they're going to be connecting from this IP address, right? They can do an SQL injection or they run remote code on your server. They will only be able to log in with the web user into the database WebDB. Even if they have the password for another user, they can't use it because it's only this user. If you have other databases on the same server that are more secure than your WebDB, they can't get to them. Again, even if they have the password, they can't get in. And likewise, if you leak the password of the web user account, because someone did a path traversal vulnerability on your website or something, they can't use that from anywhere else in the network other than your web servers. Doesn't matter, it's not possible to get there. If your DBAs accidentally configure their machine to turn off SSL, they can't connect at all. Like their connection gets rejected before it even logs in. So it's all about compartmentalization, like making sure if someone hacks you, when someone hacks you, if you make a mistake somewhere, make sure that your exposure is as small as possible. Now actually basically this, and maybe a couple of lines more because you need things like localhost over IPv6, but that's something that you can use in most simple web apps just straight out of the box. Lock it down. In particular, make sure that your super user, your DBAs, can never connect from your web server. Because if someone breaks into your network, they're probably going to start at the web server, because that's the part that's exposed to the internet, right? And if you make sure they can't escalate from there, even if they manage to guess your super user password, you've helped yourself pretty far along the way. And you want to make sure that doesn't happen. And again, if nothing at all matches, so if someone connects that not from the web server or from the DBA network, then they just can't log in. Now for that scenario, you should probably also have a host firewall, right? Because once you get into Postgres, we're going to have to parse this file. Now we've actually read the file and stored it in memory in sort of a pre-parsed order, but it's still a sequential scan throughout the file. If you have 10 rows, that's a very fast sequential scan. But it's not as fast as a kernel level firewall rule, just dropping the packet. Most of you will probably have run into this, the first time you installed Postgres. You got that wonderful error, there is no matching PGHBA row for user XYZ. Yeah, that's this guy. What unfortunately I see far too many people doing in those cases is they create one and they create a rule for 000/0, which is the entire internet. And then if we're lucky, they say prompt them for a password. And then you make Postgres just as dumb as most other databases. If you're unlucky, they say trust, which means just let everyone do whatever the hell they want, which is a really bad idea. So combined with this, so the last column will let us pick a number of different authentication methods. There is a lot of choices in Postgres. There are some that are internal to Postgres. There are some that are integrated with the operating system. There are some that are fully external. There are some that are good, and there are some that are really, really bad for using on your production system. At the bottom of the edge, there is the one that we call trust. And that one will trust everyone everywhere, right? Particularly if you combine it with one of those nice lines that says 0000/0, and then trust. That means that you just trusted everybody on the internet. I don't think that's been true for 30 years, that you could actually trust everybody on the internet. But trust really means whoever connects get to tell Postgres who they are, and they don't need to bring any proof of them. So if they say, hey, I am web user, log in. I am Postgres, the super user, log in. Right? You basically turn off all security in Postgres if you do that. Not a good idea. Now, personally, I found one actually really good use case for trust, but only one. Anyone care to guess what that one good use case would be? Where it actually makes sense to use trust? Development machine? No, I don't agree. Because then you're not developing on the same thing that you're going to put in production. If you're not testing the right thing.
Maybe if you need to reset admin password.
If you need to reset admin password, was another suggestion. That's very close, what I'd say. It's actually exactly what I'd say. I just add a restriction. If you need to reset your admin password and you're using Windows. Because if you're not using Windows, we have better ways of solving that problem. But if you're using Windows, yes, you set trust, you log in once, you change your admin password, and you turn off trust again. Right? But there's actually no other way to recover your admin password on a Windows installation that doesn't include like hex editing. And this is much better than hex editing. But as a temporary measure. And again, if you're on a Unix platform, we have better ways of doing that. Therefore, if you actually spot trust somewhere in your live database configurations in production, go fix that. I would consider that a rather critical security bug if you find trust in any running production system. It's gonna hurt. That's what it does. Now, probably the best way, and the one that we will use instead of trust to reset our admin password on Unix, is peer. This one only works over Unix sockets, which is why we have to use trust on Windows to get around it. But it only works on Unix sockets. It doesn't work if your client is Java. But for pretty much everything else, it works. And what happens is, whenever Postgres gets a connection over a Unix socket, it will ask the local kernel, saying, who made this connection? And the kernel will say, well, Magnus made the connection, or Postgres made the connection, or root made the connection, and then we'll trust that. And frankly, if you don't trust the local operating system kernel, you have a bigger problem. Right? There's nothing you can do if someone has hacked your local operating system kernel. So arguably, we can say that this is actually perfectly secure. This is the one authentication method that the only way to hack it is to already own your server. And if you do that, you can just do whatever you want anyway. Now, this is obviously assuming you configured your users correctly in Postgres. But once you did that, peer is really secure. And I don't really see any reason ever not to use peer over local Unix connections. Just always use it. It'll make you happier. And you don't need to forget your passwords. And again, if you have a password set on your accounts, you can always, the thing then is you have to SU on your operating system to be Postgres, and then connect using peer, and you can change the password. So it will just verify that you are the correct user on the operating system level before it lets you in. So it's probably the most trustworthy one. Now the simplest one, if we just assume that trust doesn't really exist because we should never use that, now the simplest way of doing authentication in Postgres is MD5. Right? This is the username password combination that everyone uses. I don't think there is a database out there that doesn't support that. It's a double MD5 hash, so we'll hash the password once on the client and once on the server, which means, in theory, it's safe to send this across the network. Personally, I'm not sure that really matters, because does it matter if your password is safe, if all the data that it unlocks is cleared out? If you don't trust your network, you should be using SSL, or VPN, or IPsec, or one of those. But MD5 is the way you go. There is also a method that is called password. That is generally not a good idea to use. There is a use case, since MD5 is double hashed, you can actually log in if you just have the hash. You don't need the password, you need the first hash. libpq doesn't let you do that, but if you speak the protocol natively, you can do that. That basically means that if you can hack into the server and steal all the files from the server, then you can also log into the server as a non-privileged user. I'm not really sure where the attack vector is at that, but in theory there is one, and password can actually help you against that. Now, password sends the password in clear text, but password combined with SSL potentially has a use case. And it's defending against someone who has already hacked your server from hacking it again. If they hacked it, you didn't notice, you didn't change your passwords, and then they can come back. But normally, if what you want is username and password, you should put MD5 in there, and everyone will be happy. Now these are the simple ones that we always include, and that are supported on all the platforms. We also have the ability to integrate with external authentication systems. Probably the most common external authentication system, not just in a Postgres world, but in sort of any world, is to use Ldap. I'm sure you all know what it is. Now internally in Postgres, or to a Postgres client, Ldap just looks like a password. Normally when we get a password into Postgres, we compare it to whatever stored password we have in Postgres. Right? With Ldap, we instead take that password and send it off to an Ldap server that you've configured, and asks it, this user, this password, is that correct? And the Ldap server basically says yes or no. Which means that we don't need any special support on the Postgres client. Anything that can speak username and password will work with Ldap. Means that it's actually very easy to get Ldap working. We have some other more advanced authentication methods that require things to happen on the client, which can be a lot harder to integrate. But Ldap is really easy. Now we have two different ways of doing Ldap authentication in Postgres. We can either use what's known as prefix and suffix, or we can use a search and bind. This is similar to many other Ldap services that allow you to have these two different ways. Hi? Okay. You get coffee in 5 minutes. You get coffee after Ldap. Now the easiest way to show that, I think, is just showing by example. So is what you put. Again, you put this in the PGHBA file at the end of the line, where the previous example had things like MD5 or peer. You just say Ldap, and then you can add a bunch of parameters that controls you how this works. So you can use different Ldap servers for Postgres connections coming in from different locations, for example. And the simplest way of doing this, we use Ldap suffix and prefix. And we basically, if we set, so in our HBA we say Ldap prefix equals double quotes CN equals. You almost always want to use double quotes when you set up the Ldap stuff, because they tend to have equal signs in them, or spaces, which is really confusing. And we say Ldap suffix equals, comma DC equals domain, comma DC equals call. That comma is very important, just like that equals sign. Now, when someone tries to log in, for example, me, my username is typically MHA from Magnus Hagander, then what Postgres will do is it'll construct TN consisting of this, CN equals, coming down there, then it adds my username, and then it just adds the suffix right there. So in this case, it constructs CN equals MHA, DC equals domain, DC equals call. Then it connects to the Ldap server, tries to bind with that username and the password that I sent to the server. And if that server matches, then I'm going to get a bind successful. If it doesn't, I'm going to get the bind failure, right? This is the simplest way of setting up the Ldap. The downside of this is all your users have to live in the same container in Ldap. And in most cases, you probably went to Ldap because you had many users. And you don't want them all to be in the same container. So for that reason, we have the more advanced way of setting up Ldap, which is the double binding format. In this case, we specified a lot more parameters. But basically, we set an Ldap base DN, which is where in Ldap are we going to search for users. In this case, I'm going to search in my entire domain, which is DC equals domain, comma, DC equals com. It's going to search the whole thing. But you can restrict this to a specific container as well, obviously. But we'll start from there and we'll do a subtree search. Then we say Ldap bind DN. This is the user that Postgres will use to log into the Ldap server. So this is not the end user, this is for the Postgres server itself. So we say the Postgres server is going to log in as scene equals Postgres, DC equals domain, DC equals com, with Ldap bind password as super secret. And then finally we say Ldap search attribute equals UID. What's going to happen here is when I try to connect, MHA, Postgres is going to connect and bind to the Ldap using this user with this password. Then it's going to issue a search to the Ldap server and say, in this container, find me any user that has UID equaling my username, the one I'm trying to log in with. And it's going to do a subtree search. And if that user is found, then it's going to get the name of that user and try to log in with the password that I supplied in the client. And with that done, it'll check the result of that bind. If the user isn't found, it just gets a login failure. So this allows you to have your users in a properly hierarchical organization in your Ldap catalog. Now for this double bind, we can also use an Ldap URL format. This is a standard Ldap URL, which is, in this case, we put the server. I should add for these two, you also set Ldap server equals to the address of the Ldap server. I just took that off the slides to make them fit. In the URL format, we say Ldap URL equals Ldap IP address, where we search, question mark, which attribute, question mark, sub for subtree search. That's a standard, RFC standard Ldap URL. In this case, we still need to give Ldap bind DN and Ldap bind password, because that's how Postgres logs into the Ldap server to figure out, or to perform this search, to figure out if the user actually exists. Yes, question? Do we have a microphone?
We, with my colleagues, have a few questions about Postgres application. And first, my question is, does PostgreSQL support security policies for passwords, for example, as maximum unsuccessful logins attempts, password difficulty, and some other like this?
Okay. So does Postgres support security policies for passwords? Postgres itself does not in built-in. There is a contrib module for Postgres that implements some of that. And of course, if you're using Ldap, for example, then it's up to it's implemented in the Ldap server. And then it has it indirectly. But Postgres natively does not.
And my second question is, radio service supported by Postgres or not?
Yes, it is. I'll get to that in just like 2 or 3 slides, something like that. So I'll answer your radius question later.
Thank you.
So the last note about Ldap is Ldap by default is clear text. Okay? Postgres will make a clear text bind to the Ldap server. If you don't like that, Ldap TLS equals 1. Then Postgres will make an encrypted connection to the Ldap server. In both those cases, whether you have Ldap TLS on or off, in both those cases, the password is in clear text from the Postgres client to the Postgres server. The Ldap TLS parameter only controls Ldap server to Postgres. If that's a problem, it might not be a problem. Your client might be local on the same machine. But if that is a problem, use host SSL or VPN or something. The Postgres Ldap provider will send it in clear text over whatever channel happens to be available. As we mentioned, password policies will be whatever you have in your Ldap server. Postgres can't and won't try to do anything about that. And it's also important to know we only do authentication. Okay, it would be really convenient if Postgres could, for example, populate the list of roles based on which groups you're a member of in Ldap, but we can't do that. It will only verify that, I am MHA. That's it. It can't copy any level of permissions or anything down from Ldap. Today. Maybe we'll get that at some point, but we don't have that ability today. I have a couple of more authentication methods to go through, but they're signaling me from the back that you guys need coffee. So we'll take a break and we'll get those when we get back. How long is our break? You guys control that in the back? How long is the break? 15 minutes break. Okay. So 15 minutes, coffee and tea and things are outside. I'll see you shortly.